Okay, chapter 12 is what we're going to start now. We're going to talk about logarithmic and exponential functions. 12.1 is all about exponential functions, and it's kind of like a preliminary thing that we need to know when we get to logarithms. So suppose that you had a chance to work for 30 days and could choose one of two methods of payment. Method 1 is where you could choose to be paid $1 for the first day, $2 for the second day, $4 for the third day, $8 for the fourth day, and so on, with the amount doubling each day. Or method 2 is where you could just receive $1 million in one lump sum. Which method of payment would you prefer? Okay, some might be drawn to the $1 million in one lump sum, but you may be surprised about method 1 here. So the following table it shows you how method 1 is changing throughout these 30 days. Okay, so $1 the first day, $2 the second day, $4 the third day, $8 the fourth day, and so on, with it doubling each day. And at the end of 30 days, we have more than $500 million. Notice that the total grew pretty slowly at first there, and very quickly towards the end of the 30 days. Okay, so obviously somebody would want to choose method 1 rather than just choosing $1 million. Okay, this is an example of exponential growth, which is based on exponential functions. In chapter 9, in section 9.2, we had talked about our laws of exponents. This was in your notes from earlier. We'll need to make sure that we know our laws of exponents for working with exponential functions. So I'll be referring to the laws here and there. Okay, let's take a look at the definition of an exponential function. An exponential function is a function of the form f of x equals c times a to the x, where a is called the base of the exponential. A has to be a positive number. Can't be 1 though, okay, because of law 6. 1 to any power is 1. Okay, and if a was 1, you would have f of x equals c. F of x equals c would just be a horizontal line at a height of c. And c cannot be 0. Okay, if c was 0, 0 times anything is 0, and you'd have f of x equals 0. F of x equals 0 would be a horizontal line at a height of 0. We're not doing anything with horizontal lines at the moment. Okay, so these would be the conditions on an exponential. The domain of any exponential is all real numbers. Okay. Let's take a look at problem 1. Graph the exponential functions f of x equal 2 to the x and g of x equal 1/2 to the x. And then we'll state the domain and the range, and I'll mention some other things here. X can be anything, right? The domain is all real numbers. So I've got a table set up here, and I'm just going to start plugging in some numbers. So like if x is negative 3, 2 to the negative third, yeah, that's the same as 1 over 2 cubed, or 1/8, using this law here. So here's negative 3 1/8 on the graph. Let me just graph f of x first, and then I'll graph g second. So if I let x be negative 2, 2 to the negative second, that'd be the same as 1 over 2 squared, or 1/4. Okay, so here's negative 2 1/4 on the graph. If x is negative 1, 2 to the negative first is 1/2. There's negative 1 1/2. If x is 0, anything to the 0 power is 1. That's law 7. Okay, so this curve is going to cross the y-axis at 0 1. If x is 1, 2 to the first is 2. Okay, so here's 1 2 on the graph. If x is 2, 2 squared is 4. So here's 2 4 on the graph. And then we'll just take one more. If x is 3, 2 cubed is 8. So here'd be 3 8 on the graph. Now what's happening with f of x is starting in quadrant 2. You're just above the x-axis here, and you're rising slightly. You'll pass through the y-axis at 0 1, and then after you cross at that spot, the curve is going to shoot upward and outward into quadrant 1. Okay. Now, x can be anything, positive, negative, 0, it doesn't matter, okay? Notice that in this table, we will never have a negative come out of the calculation, and we will never have 0 coming out of the calculation. That's because x is in the power. So what that means to us is that this curve, while it's heading outward towards the left, will never get to the x-axis. Okay, since you're never going to have 0 coming out of the calculation, you will never get to the x-axis. So there's a boundary on the x-axis. An asymptote is a boundary that the graph approaches but will never get there. Okay, so we would say that there's a horizontal asymptote right on the x-axis, and that's a feature of an exponential. There will always be a horizontal asymptote on the graph. Let's graph g of x now. G of x is equal to 1/2 to the x power. I'll just use these same 7 x values that I already had set up for when I graphed f of x, and I'll use them to graph g of x. So like if x is -3, 1/2 to the -3rd, that would be the same as 1 over 1/2 cubed, or 1/2 cubed is 1/8, right? So if you have 1 over 1/8, that would be the same as 8. Okay, here's -3, 8 on the graph. If we let x be -2, 1/2 to the -2nd would be the same as 1 over 1/2 squared, or 1 over 1/4 is the same as 4. Okay, here's -2, 4 on the graph. If x is -1, 1/2 to the -1st would be 2. Here's -1, -2 on the graph. If x is 0, anything to the 0 power is 1. So this curve is going to cross the y-axis at 0, 1. If x is 1, 1/2 to the 1st is 1/2. So here's 1, 1/2 on the graph. And if x is 2, 1/2 squared is 1/4. Okay, here's 2, 1/4 on the graph. And then if x is 3, 1/2 cubed is 1/8. So here's 3, 1/8 on the graph. Now this curve is going to be starting off in quadrant 2, and it'll be curling in towards the y-axis. It's going to cross the y-axis at 0, 1, and then it's just going to kind of fizzle on out. It'll get closer and closer to the x-axis, but it will never get there, okay, because we will never have 0 coming out of the calculation. We will also never have a negative, okay. So there's going to be a horizontal asymptote on the x-axis, okay. The curve is going to be getting closer and closer to the x-axis, but it will never get there. Now, I've already mentioned that the domain of an exponential is all real numbers. I can let x be anything I want, okay? The domain of f is all real numbers. The domain of g is all real numbers. The range of a function y equal a to the x is going to be all positive numbers, okay? Notice that I'm only getting positive numbers coming out of this, right? I'm never going to get 0. I'm never going to get a negative, with x being in the power there. Now, in general, whenever you have an exponential, the graph is going to kind of resemble either f of x or g of x. If the base is a number bigger than 1, a can't be 1, remember, but if it's bigger than 1, the graph is going to resemble what we see here with f of x, okay, where it's going to be rising slightly, it'll pass through the y-axis at 0, 1, and then it's going to shoot upward and outward into quadrant 1. The bigger the base, the bigger the shot upward after you cross the y-axis. So like if I were to graph y equal 5 to the x, I would have a bigger shot upward after I cross 0, 1 than what you see here with when it was y equal 2 to the x. Now if the base happens to be less than 1, but still positive, then the graph is going to resemble what we see here with g of x, okay, where you'll be starting off in quadrant 2, you'll be curling in towards the y-axis, you'll cross the y-axis there at 0, 1, and then you'll be approaching the x-axis, again with the understanding that you'll never get to the x-axis though. Okay. The next thing to talk about is, so we're going to have to be familiar with the number e. Here's a definition. The number e is used to represent a fundamental irrational number with decimal approximation E is roughly 2.72 if you go nearest 2 digits. I've gone out quite a bit though. The function f of x equal e to the x is called the natural exponential function. And this is arguably the most common exponential function. What I mean by that is, so there's significantly more mathematical formulas and calculations that you're going to be doing when the base is base e rather than any other base. Okay, so you're going to see base e come up more than base 2, more than base 1/2, more than base 5, more than any other base. You're going to be working with base e. Now, we'll see later on that e is the base of what's called the natural logarithm. Okay, and there's a huge connection with exponentials and logarithms. We'll talk about that in the next section. Okay. Now, of course, an irrational number is one that cannot be expressed as a fraction. Pi would be an example of an irrational number. There's no way to write pi as a fraction. Okay, same deal with e. There's no way to write this number in fractional form. Irrational numbers have decimal expansions that never terminate or repeat in a pattern. So, problem 2. Let's take a look at the graph of f of x equal e to the x. Okay, and then we'll state the domain and the range. Now, most calculators have an E button on it somewhere. It's just locating it. Okay. On the TI-30 model, if you were to hit second ln, it'll set you up with e to a power. A lot of calculations that we do with e involve powers. Okay, so if I just had like e to the the number e, I'd want e to the first. And there's that decimal that you had seen earlier there in the definition. Okay, and of course I can type in any power that I want there. On the graphing calculator, the TI-84 model, if you hit second and then ln, it'll also set you up with e to a power. Okay, so like here's e to the negative second would be roughly about 1.4 if you go nearest 2 digits, and so I'm getting that number there. Most calculators have an E button, as I mentioned. Even the cheap, $5 Walmart calculators have an E button. It's just locating where it's at. Some of the models will have an E button there, okay, and some of them are going to be where you hit second and then like an LN button or something, okay. If it's got an LN button, it's almost certainly got an E button. Okay, I'd be kind of surprised if it wasn't there. So anyway, we're going to graph this function, and I've set up a table. Remember that the domain of an exponential is all real numbers, so I can let x be anything I want in the table. Okay, I'm starting with x equal negative 2, and I've already typed that. E to the negative second is roughly 0.14 if you go nearest 2 digits. So here's negative 2.14 on the graph. If we let x be negative 1, next, e to the negative 1 power is roughly about 0.37 if you go nearest 2 digits on that. Okay, so here's negative 1.37 would be right about there. If x is 0, anything to the 0 power is 1, so 0, 1 would be on the graph. If x is 1, we get roughly about 2.72, or the number e would be the exact. Okay, so here's 1 e, that point. And then if you let x be 2, e squared is roughly about 7.39 if you were to check that in the calculator. Okay, so the output values are going to be getting very large once you start selecting positive numbers bigger than 1. So using these points that are on the picture, I can then draw on the curve. The curve is going to be in quadrant 2. It'll be just above the x-axis here, rising slightly. And it's going to pass these points. It's going to cross the y-axis at 0, 1, and then it's going to shoot upward and outward into quadrant 1. Okay. Again, you will never have 0 coming out of the calculation. You'll also never have a negative, okay, with x being in the power. So the range is going to be all positive numbers. Now, just an observation, before I even drew this, I probably could have expected a curve to, you know, to be very much like what we did here in the case of y equal 2 to the x. Okay, like here's y equal 2 to the x, and I've already got that, you know, that was what we did in the first problem. The reason why I would say that is because e is a number that is very close to 2. Okay, so if you already know what y equal 2 to the x looks like, you can probably at least have an idea of what y equal e to the x looks like. I mean, notice how similar these two curves look. Okay. F of x equal e to the x is the most common exponential function. Okay, and I mentioned that already, but you know, just how often we work with the number e for various things. It's definitely an important number in math. So why don't we'll stop the video there, and then I'll talk more about exponential functions in the next video.